for that, let me just get started with this very generic notion of quantum entanglement that we have. Or this is a very popular notion, which is of course not exactly correct, but this is a very popular notion that if you have two entangled particle system, and if we then disturb one of the particles, then both the particles actually get disturbed as a result. So this disturbing one affecting the other one, this was definitely not liked by especially Einstein, and Einstein with his other collaborators Podolsky and Rosen, they actually objected to this kind of phenomenon, which actually points to non-locality. And they, in fact, in 1935 they actually wrote a paper where they used this aspect that actually shows up in quantum mechanics. They used this aspect to actually question whether the quantum mechanical description in terms of wave function, whether that description is even complete. And then later there's a lot of work on that, but the main point I just wanted to bring right now is that Einstein, Podolsky and Rosen, they basically objected to this kind of phenomenon. So, but this is a kind of a popular notion of how one thinks about entanglement. Of course, this is not exactly correct, but it actually conveys the idea to a pretty good extent. But in this course, we will do entanglement with all its mathematical rigor to actually know what exactly it is, and also discuss these kind of interpretations that actually come out in a lot of development that happened after Einstein's objection. And then in fact that led to this entire field of quantum information that actually came as a result of kind of studying these foundation aspects of quantum mechanics. So we will get to entanglement after a few lectures in this course, but I just wanted to kind of bring it here. But for now we'll go to the basics of quantum mechanics and coherence and then build it up from there. So to begin, let me just go back and point out what are the main differences between classical and quantum mechanics. The differences that I have here, they are not necessarily all separate differences. There can be the overlaps, but I'm just putting it in these points to make things clearer. So first main difference between classical and quantum mechanics is determinism. So classical mechanics is in principle deterministic, whereas quantum mechanics even in principle is indeterministic. And that is in the sense that its future evolution cannot be predicted. So classical mechanics is guided by Newtonian mechanics, and if you know the initial condition, the final the outcomes, the final values of the physical variables can be predicted very accurately. But in quantum mechanics, that is not there. Even if we have enough information about the initial condition, even that is not enough for anybody to be able to predict its exact future evolution. So in that sense, quantum mechanics is in principle indeterministic. So one of the example we can see is in an experiment, where one has a light source, single photon source, this photon coming from this light source, and then going through some aperture and then hitting some screen. Now the question is, where does a photon that is coming out hits this screen? Of course the light is everywhere, so it can hit the screen anywhere, but where exactly it hits, that cannot be predicted. So that is completely indeterministic. This indeterminism need not be a very bad thing. In fact, there is a very nice application of this indeterminism within quantum mechanics, and that is that this aspect can actually be used for making true quantum random generators, and that is using a beam splitter, and that's how it works. So this is a beam splitter. The beam splitter just splits light field into two. But when it comes to quantum mechanics and single photons, then a single photon, as we know, cannot be split. It has a fixed energy, h bar omega, for a frequency omega, and that cannot be split. So then what does a beam splitter do in that case? In that case, beam splitter either sends this particle here or there. And if the photon passes, just transmits, then the entire photon comes up here, or the entire photon comes out here. So it's not that it's half. So the randomness is in whether it ends up here or it ends up there. So that's where the randomness is, and this is truly random. So if if the photon comes out here, we call it 0, and if the photon comes out here, we call it 1. Then the random number generation happens in the sense that you just send in these photons one by one, and whether it comes out here and there, we just then generate just a string. So, if the photon then for few photon, if we just send them, then that we generate a string of 0 and 1, and that is truly random in the sense that no matter how long one writes this string, it never repeats itself, and that's a true random number generation. And this definitely has an application in quantum information. Okay, so the next difference is the measurement or the effect of measurement. In classical mechanics, an act of measurement does not affect the system. A system, one can extract information about the system by doing measurements on the system, but that doesn't affect the system at all. But in quantum mechanics, within quantum description, an act of measurement changes the system in general. There may be situations, there may be systems, states for which the measurement doesn't affect it, but in general, it does affect the system. So, for example, if one has the state of the system given by psi, and if one does a measurement, then after the measurement, one might just find the state in some state psi 1 or psi 2 or psi n. And where psi n is some from 1 to n, where n is the dimensionality of the Hilbert space in which this state exists. So, one example of this could be that the same example of photon hitting the screen. Now, these individual dots, these are like the, before the photon hits the screen, it has a possibility of being anywhere, but once it hits the screen, then we know that it is actually here. So, it's like this psi, the state before the screen, when the photon could be anywhere, but the psi 1 and psi 2, these are the photonic states after they have been detected at these these localized locations. So so this is an example of state collapsing into these states after the measurement. Now, one exception to this is that when the system is in one of the eigenstates of the measurement operator, then this system doesn't change. So, if the state of the system is some psi m, and if it is the eigenstate of the measurement operator, then even after the measurement, the state remains in the same state psi m, it doesn't change. An example of that we can understand through what is called the polarizing beam splitter. So, suppose a polarizing beam splitter we can see here as a measurement device, and what it does is that it sorts a photon based on its polarization. If it's a vertically polarized photon, it will transmit the photon through it, but if it's a horizontally polarized photon, it's going to reflect. So, for this polarizing beam splitter, if we have a vertically polarized photon coming in, then that's in a sense the eigenstate of this measurement device, and then so if it's a vertically polarized photon, it will just go through it and remain vertically polarized, no change in the state. So, that's one example where we see that if the state of the system is one of the eigenstates, then the measurement operation doesn't change the state at all. Now, the other difference between classical and quantum mechanics is the equation of motion. In classical mechanics, the equation of motion are written in terms of real variables such as position, momentum. For example, Newton's equation we write in terms of position, momentum. Maxwell's equation we write in terms of real electric field. The electric field that we write in Maxwell's equation is actually real electric field. But in quantum mechanics, the equation of motion are in terms of an abstract mathematical quantity called the wave function. A wave function is, it's not a real quantity like position, momentum, or even electric field. It is just some abstract mathematical quantity, and the equation of motion, which is the Schrodinger equation within quantum mechanics, that is the equation of motion is in terms of psi, that wave function, which again is just a mathematical quantity, and there's nothing real about it. The wave function as is, there's nothing, it's not as real as you have the momentum and position and so on. So, the equation of motion, again, things are very different in classical mechanics and quantum mechanics. Then the next difference is the duality, the dual nature. In classical mechanics, there is no duality. A system behaves either as a particle or as a wave. So, it's very clear whether the system we are talking about, whether it is a particle like or whether it is a wave like. If it's a particle-like situation, then we use Newton's equation, and that describes the evolution of a particle. If it's a wave-like system, then we use Maxwell's equation, which describes its evolution. So within classical mechanics, a system is either a particle or a wave, and depending on what it is, we choose appropriate equation to describe its evolution. But in quantum mechanics, the duality is at the very core of it. In fact, that's the characteristic feature of quantum mechanics, that a particle is both wave and particle at the same time. This is very difficult to kind of understand intuitively, but this is what it is. I mean, that's the best explanation people have so far, that with a quantum system is particle and wave at the same time. So to address this wave particle duality, to address a system which is wave and particle at the same time, either Newton or Maxwell's equation, that is not enough. We need to use Schrodinger equation, which is given like this. So again, even if a quantum system is showing only its particle properties, that means if there is a quantum system, but if we are only looking at its particle properties, then all of that can actually be explained using classical equations for particle. Again, if there is a quantum system of which we are only interested in wave properties, then a Maxwell's equation can do the job. But if we are looking at the true quantum characteristic features, then the wave particle duality is there, and then to be able to explain all the manifestations of this wave particle duality, we have to use Schrodinger equations. There is no other way. Yeah, so this in a sense describes the simultaneous existence of wave and particle properties. Okay, so one last difference, superposition principle and interference. This is again a very important difference, and I will do that in much more detail in the later slides, but I just wanted to kind of bring it here to point out exactly the main difference. So classical mechanics, superposition yields a definite state. So if you have this is like a vector addition, if this is a state, this is a state, then that yields, there's a new superposition state. But within quantum mechanics, in some sense, superposition does not yield a definite new state. It just changes the probability of being found in the basis states. For example, if we have a superposition of states like this, which is superposition of vertical polarization and horizontal polarization in some proportion A and B, then what we get is not necessarily a new state, but this state basically means that we have the photon, we have vertical photon with probability A square and a horizontal photon with probability B square. That means if we do the measurement on this, if we do a measurement on this state to check its polarization, we'll find that the system is vertically polarized with A square probability and horizontally polarized with B square probability. Of course, the total probabilities, the total probability has to be equal to 1. Now regarding interference, so in classical mechanics, the description of interference is based on division of amplitude, and division of amplitude necessarily implies division of energy. This is kind of inbuilt. However, in quantum mechanics, the description of interference is not in terms of division of wave amplitude. It is based on the division of wave function. Now, it turns out the division of wave function does not imply division of energy. Of course, this is because a photon cannot be divided. So interference, that is explained in terms of division of, dividing amplitude and then combining, superposing back again. In quantum mechanics, we do that in terms of dividing wave function and then combining it back again. However, this dividing the amplitude, which implies dividing the energy of the incoming stuff, that is not the case here. That dividing the wave function does not imply dividing the energy of a photon. So we will do that in much more detail, but I just wanted to bring it here in order to point out the main differences between classical and quantum mechanics. So now we actually go back in order to get deeper into looking at some of those aspects of quantum mechanics. We want to go deeper, and we want to go at the times when people were asking this question as to what is light, because it all started from this question as to what is light. A light, as we know, can be a wave, it can also be particles. and it can, in fact, in 17th century, light was actually made up of particle. That was a theory that was existing at the time, Newton's corpuscular theory, and that existed for quite some time. Then around 1900, due to experiments by Young's double-slit experiment and others, experiment on the wave properties of light, then those experiments could not be explained by Newton's theory, and then at that point it was understood that light was actually a wave. But then in 1900, after Planck's hypothesis and photoelectric effect and so on, after these experiments and effect, it became very clear that light is wave as well as particle. Now, this is a very absurd and non-intuitive conclusion, because a wave, as we know, is something that is delocalized. It is not somewhere. In fact, a wave, if we look at it, it is something that is actually everywhere. Of course, this is delocalized, and in the biggest sense we can see it is actually everywhere. But on the other hand, a particle, it is somewhere. When we think of particle, we think of some solid object or some such thing which is just somewhere. It has a finite size, finite location and so on. So a particle is something that is somewhere, but a wave is something that is everywhere. So now when we say light is wave as well as particle, we mean that light is something that is somewhere as well as everywhere. Now, how is that possible? I mean, this is as absurd as it gets, but is it true? Yes, it is true. Does it make sense? It doesn't make sense, but it is true. So this is in fact the best understanding we have of light or of any quantum system, because it is wave as well as particle, and that immediately implies that the system can be somewhere as well as everywhere at the same time. So this is the current understanding of quantum system, and let's say photon in particular. We'll be discussing mostly photon as the quantum system. So that's the understanding. Okay, so now let's get in some more detail with the interference that we have here of light. So this is the famous Young's double-slit experiment. So if you have a source of light, and here I am describing light when we see it just as a wave. This is a classical wave interference. I mean, everybody's kind of should be taking those who are taking this course should be actually familiar with this. So we have a source, and let's say if we make the light coming out of this source through this opening, this slit, then on the screen over here we'll have more intensity in the center and not so much in the side. So it kind of gradually decreases towards the side. So now if we, let's say, have another slit, then all that happens is that this entire intensity pattern just gets shifted, probably by the same amount that the slit was shifted. But if we have both the slits together, then it is not that we have just both the intensities added together and that is a resultant intensity. No, what we are seeing here is that it's the interference pattern that we have, which is the periodic variation of the intensity as a function on the screen location. So this phenomenon is called interference, and of course there has to be some conditions which need to be satisfied. For example, the light coming at the slits needs to be coherent with respect to each other, then only the interference will happen, and those conditions we'll look at in detail in this course. But the point is that if we have this light coming from these two slits, then it's not that they just get added up, it's just they are actually produce interference pattern. And the point is that this interference pattern is basically a continuous periodic variation in intensity. And this is one picture that actually was recorded in my own lab. So this is a real picture that is recorded for such experiment. Okay, so how do we explain this interference? We explain this interference in terms of the interference of light or superposition of light coming from this slit and from that slit. So the way we do it is we say, okay, we have this light field coming in, the electric field, we divide its amplitude between this, and so some of the amplitude goes through this, some of the amplitude goes through this, and to the extent that we divide the amplitude, we have the energy associated with it, the division of energy, and then we superpose these amplitudes at this point to explain the interference pattern or to generate the interference pattern. So that is a classical explanation description of interference effect and pattern. Now in quantum mechanics, we have the ability to have a source that emits single photons. Now, a single photon by definition has fixed energy and that cannot be divided. So, now when this photon arrives at this set of two slits, then it has to decide whether it wants to go through this slit or through that slit. Now, quantum mechanics does not allow this photon or the energy of this photon to be divided. So, this entire photon has to go through this or has to go through that. But how do we know that this actually happens? In fact, that we can see by looking at what happens at the screen. So, whatever photon at whatever frequency we are seeing, we can check the screen that this entire photon actually gets detected at some location of the detector. So, that is, in a sense, it says that we haven't divided the photon, and the entire photon goes through this or through this slit. Now, the question is, if the entire photon goes through this or through that, then what interferes? But let's first see if we actually even see the interference. So, this is the real images, real experimental images taken in the lab, where we are sending these photons one by one and looking at the screen, recording these photons at the screen. Now, what do we mean by one by one? One by one meaning these are the single photons are coming from the source, but their rate is so low that within the detection resolution time of the camera, there is only one photon or less than one photon on an average in the system. So, there is always within the camera resolution time, there is only one photon in the system. So, in that sense, it is one by one, and that ensures that we have single photon kind of experiment. So, here we see we have taken about 10-12 photons that have hit the screen. If we collect few more, then that's few more photons, and now we see these are several millions of photons collected, but we could see these are still scatter plots. We can still see the dot. These are not continuous intensity distribution, but even with the scatter plots, we see there is a nice interference pattern that has emerged. And in fact, the periodicity of this pattern is same if we did this experiment at high light level and had these slits at the same location with the same width and separation and so on. So, this is a single photon interference pattern, and as it is still dotted and scattered and not a continuous distribution. Of course, if we continue collecting these photons for several millions photons, then eventually these scatter plot will, just because of the density, they will become same continuous distribution as we see in the case of classical. Okay, so now how do we explain superposition within quantum theory? So, first just few facts about this experiment is first the photon, we see that photon goes through slit 1 or slit 2, that's for sure, because we see a dot on the screen, and that dot pattern comes one by one. Of course, the photon hits the screen at very localized point, and photon distribution is the interference pattern. So then there's people also look at, this can be a natural question that if one looks at or tries to put an effort and put some experimental apparatus just to check whether the photon goes through this slit or that slit, then through that effort one can definitely find out whether the photon goes through this or that. But this effort by which one actually gets its information, which is called which slit information or the particle information, this itself destroys the interference pattern. So, any attempt that we do in order to get the information about which slit the photon goes through, that will destroy the photon's ability to interfere, and this is known as Bohr's complementarity principle. So, the best explanation now as to why the interference happens is that comes by Dirac, and he then says, this is in his book Principles of Quantum Mechanics. This is a very good book. He says that each photon then interferes with itself. Interference between two different photons never occur. So, so this is a single photon, it has to go through this or through that. So, in each event, either it goes through this or it goes through that. So, what interferes? So, the best explanation that Dirac has, that says each photon basically interferes with itself, and that actually is the best explanation that we have. In terms of math, the way we do is that we say that okay, this time it is not the division of amplitude, rather it is the division of a wave function. And of course the division of wave function does not imply division of energy, because we know for sure that the photon either goes through this or that, and that we can see by just detecting the photon one by one. And of course the interference happened because we superpose the wave function. Okay, so to summarize superposition within classical wave theory and quantum wave theory. So superposition in classical wave theory, the way it is explained is in terms of division of division of amplitude, and this division of amplitude implies division of energy, and then the superposition of amplitudes yields the interference pattern. In quantum mechanics, the division of wave function is what happens, and then but that doesn't imply division of energy, and the superposition of wave function is what gives the interference pattern. Now the classical wave theory, it is actually fundamentally incorrect, but it is definitely applicable at highlight level. So we need classical theory at highlight level. At classical highlight level, the levels, the classical theory can explain all the results that we see in the lab. But if you use the classical theory at single photon levels, it is just inadequate. It is not able to explain. So it is fundamentally incorrect, but I mean at highlight levels we don't need anything more than classical theory, so this is perfectly fine. But quantum mechanics, it is fundamentally correct. It is correct at every light level, whether it's a single photon level or very high intensity level. So it is fundamentally correct at every light levels, but we may need it only at the single photon level, because at highlight level, if the classical description does it, and since it is easier mathematically, then one basically chooses to use classical description and not the quantum description. So it is just for the ease of description that one uses classical at the highlight level, but fundamentally the quantum description is correct and the classical description is actually incorrect, and so we have to keep this in mind. Okay, so far we have just seen Young's double slit experiment. This is the experiment, we call it spatial interference, that the interference happened in the spatial domain. I just wanted to also bring out one interference where interference is happening in the time domain. The superposition is happening in the time domain. And through this experiment, I also want to kind of revisit and discuss the Bohr's complementarity principle and what are its implications and what it means. So we have seen the Bohr's complementarity principle is that if we try to find out which slit information as to whether the photon went through this slit or that slit, then just the act of doing that makes the photons lose their ability to interfere. So let's look at the same thing in this time domain experiment. So here we have a laser, single photon source that emits 45-degree polarized photon. Now what is a 45-degree polarized photon? So a 45-degree polarized photon is basically superposition of horizontal and vertical photon. So if I am writing in the state format, the superposition of, I am putting 1 over root 2 to kind of make sure it is normalized. Okay, so a 45-degree polarized photon is essentially a superposition of horizontal and vertical. And as we can see, as the state is written, as we can see, if you make a measurement here, a 45-degree polarized photon means that it has a half the probability of being found as horizontal and half the probability being found as vertical photon. In fact, maybe if we can do the vectorial, this is the vertical. That's the horizontal. That's 45, and this angle is also 45 degree. Okay, so now this 45-degree polarized photon, it encounters a polarizing beam splitter. Now polarizing beam splitter, as we have discussed in the I think the first few slides, is a device that splits the field based on its polarization. So if it's a horizontally polarized photon coming in, then it will let it transmit, but if it's a vertically polarized photon coming in, then it will reflect it. Now, a 45-degree polarized photon has 50% chance of being found as horizontal and 50% chance of being found as vertical. So when it is horizontal, then it goes this way, but when it's vertical, it goes this way. Now they combine back. This is the splitting of the wave function or amplitude. Now when they combine back, then here we are using non-polarizing beam splitter. A non-polarizing beam splitter does not distinguish between the polarization of the photon. It lets everything. So if it's a vertically polarized photon coming in, it has the 50% chance of getting transmitted, 50% chance of getting reflected. Again, this horizontally polarized photon has 50% chance of getting transmitted, 50% chance of getting reflected. So if we look at here, we can have a photon coming this way, or we can have a photon coming this way. So now let's say if we come in with a polarizer, a polarization detector. So if we detect the photon to be horizontally polarized, then we know for sure that it came this way. But if we detect the photon to be vertically polarized, then we know that it came this way. So in this situation, we in principle have the capability of finding out whether the photon came this way or that way, and hence because of this there will be no interference. If we put a screen and look at it, there will be no interference, and that's the Bohr's complementarity principle. So now the question is, in this situation, since we do have the information about which slit or which path, we don't have any interference pattern, but can we get rid of this information, and if we can, then will the interference come back? So first of all, how do we get rid of the capability that lets us find out which way the photon actually came in? So we can actually put 45-degree polarizer, so a polarizer at 45 degree. Now what this polarizer does, so if this is a polarizer at 45 degree, then only thing that actually passes through it is a 45-degree polarized photon. Now just as 45-degree polarized photon can be written in terms of vertical and horizontal, similarly a horizontally polarized photon can also be written in terms of 45 and minus 45-degree polarized photon. So if this H photon comes here, then it has 50% chance of getting transmitted through this polarizer because it is at 45 degree. Now if it's a vertically polarized photon, it also has 50% chance of transmitting through this polarizer, but the point is whether it is horizontal or vertical, if it transmits, it becomes a 45-degree polarized photon. So if we are here, and then even if we have a polarization detector, and let's say we find that the photon to be 45-degree polarized, now with that information we just cannot find out whether the photon came this way or that way, because if we find it is 45 degree, then it would have come this way, or it could have also come this way. So now just putting a polarizer at 45 degree removes the capability with which one could actually find out the which slit or which path information. So the moment that ability is gone, the interference actually comes back. So that's the Bohr's complementarity principle in the context of temporal interference. Okay, so this is I actually now want to show a few slides. In fact, these are the experiments that we have done in our own lab, and these are the single photon interference experiment. This is just to show that yes, we can actually see the single photon experiments in the lab, and this is well within what can actually be done. So this is in the spatial domain. This is just the same Young-Slocum experiment, and this is the kind of interference pattern we see. Now what we see in experiment if we do with single photon, so here is a video of the detection that we have collected. Okay, so this is more of a symbolic experimental setup. What we have used actually here is a single photon source by attenuating a helium neon laser to a very low intensity, so that we have only one photon coming in within the detector resolution time, and that goes one by one through this double slit scheme and then gets detected at the detector. And so this video is actually recorded over 1 hour, but I have it here for over just 1.5 minutes. So let's run the video. Okay, let me pause it here. So what we are seeing here on the screen, these are the single photon. These are photon coming in one by one. So each dot is the one photon hitting one pixel. So this is just one pixel of the camera that gets So this is individual pixel of the camera that gets hit by single photon. Now if we just keep running the video, then we see that these photons are coming in just one by one. Initially we are keeping the video at a slower speed, so you see photons coming in one by one, but now then the speed will actually increase, because this was actually recorded over 1 hour, and we have compressed that to within 1.5 minutes. So we see that these photons are definitely coming in one by one. That is the main point. And now if we look carefully, some pattern has already started to emerge. We see some more, the photon density to be more here than over there, and as it kind of continues, we can see that. You can also have a situation where two photons are coming at the same pixel, that it has a finite possibility, for example this pixel and that pixel. But overall we still see this as scatter plot, and as the video progresses, we can see this interference pattern very clearly. That but still this pattern is not a continuous distribution of intensity. It is the dotted structure, but even with the dotted structure, now we can move the we can see it very clearly that this is the interference pattern, and this interference pattern with the dots shows that this is single photon interference, that photons came in one by one, but still we see interference pattern. And the question is, what interferes with what? There is no answer to that, and the best answer is that yes, a photon actually interferes with itself. Okay, so this is the experiment in this Young's double slit kind of setup, but we can do some more interesting stuff. And here I am just doing this interference experiment in angle. Instead of doing the in space, we are doing this angle. This we will do in much more detail in the course, but right now I am just kind of bring it here to show the variety of situation in which one can see interference. So here, instead of, as in the case of Young's double slit experiment, instead of light coming from the two slits interfering, we have two different modes of light. These are called orbital angular momentum modes. This is actually a orbital angular momentum mode with LH bar orbital angular momentum. This is the with minus LH bar orbital angular momentum. We will get to these points in detail in this course. But the point is that if we superimpose these two modes, then we get a pattern which has the intensity dependence in the phi domain as 4 cosine square L phi by 2. So if we do it with L equal to 4, then this is the pattern actually we get. We can actually see this. So I want to show this experiment at the single photon level. So from the experiment, again we see these photons coming in one by one. Again, this video was recorded over about more than 1 hour, and this is for 1 hour 49 seconds. So now we see these individual photons are coming one by one. Right now it's completely scattered, no pattern, but as time progresses, these will start to make some pattern, and then we'll see what kind of pattern. We can just and quickly. Now we already see, I mean this is the kind of pattern we are expecting, because this is at the highlight level, and we already we are starting to see these 8 lobes, which are this. So these 8 lobes is what's emerging. Let's just continue, and now we can see very clearly that this is the kind of pattern that has emerged. So I mean there's no difference between this experiment and then the last one. This is the variety of interference that one can actually see. In fact, it can be even more general, and here is a very generic setup. Let's say I have a light field coming in, and then there is a device called SLM, spatial light modulator. All it does that it can simulate any aperture, not just Young's double slit, but any aperture complex, or in any complex aperture it can simulate. And then what happens if you put a light on some aperture, and if you go to the far field, then what we see in the far field is actually the Fourier transform of this. Again, we'll do this in detail, but I'm just pointing out that a very generic interference feature is that you have an aperture in the form of some shape, amplitude and phase, and once the light diffracts off of it, then in the far field what you get is a Fourier transform of the aperture. Now here, this is just an interesting experiment we have done. Here we are putting such a structure, such an amplitude and phase aperture structure in the SLM, the Fourier transform of which looks like this stick figure. Okay, and then we change this the aperture every few times a second, so that again the Fourier transform and hence the stick figure actually changes. And then let's see see what we get here. Let me just run the video. Okay, so all we are doing is just changing this interference pattern, sorry, this aperture few times a second, and then that changes the output pattern. But the main point is these are still dotted structure. There's over 10,000 photons that are actually making this structure. And then of course you can handle those photons exactly the way we handle the classical field, but this pattern is again, just I'm saying, the dotted structure with about 10,000 photons. So we actually call this dancing photon. In fact, I have put all the last 3 videos that I have shown here on this YouTube channel, and in fact this will be the channel for this course. All the course lectures will be uploaded at this YouTube site. Okay, so now we come to the end, and again quite often I get asked as to why do photons not interfere. This is a very common question, as to why do photons not interfere when they go through a single slit. Answer is, in fact, they do, and in that case interference is called the diffraction. Maybe I can so when we have a single slit, for example, then we have light coming from all these different points, and then what one sees at the screen is a light coming from all these different points, and then we don't have a superposition of just psi 1, psi 2, but light coming from all these different points. So this continuous superposition it also gives interference, and in that case it is called diffraction. The other question that gets quite often asked is the single photons hit the screen one by one, but how do we know that they went through only one slit in a Young's double slit experiment? So this is already answered through Bohr's complementarity principle, but the question as it is actually impossible to answer, because we cannot find out simultaneously which slit or which path the photon actually took inside interferometer, and as well as see the interference pattern. So that is actually not possible. To the extent that we have which slit information, to the same extent the interference visibility actually decreases. So, and that is the idea of Bohr's complementarity principle. So it is, yes, it is impossible to find out both this simultaneously, whether the which slit information and also seeing of interference pattern. So one thing I would like to comment here is that in this interference of waves and particles, it is although I started by saying this is the difference between classical mechanics and quantum mechanics, but at least in the context of interference, it is always best to look at things in terms of waves versus particle, and instead of as classical versus quantum. So we have wave mechanics to explain waves, we have particle mechanics to explain particles, but when we have both these properties existing simultaneously, that's when we need quantum mechanics, and that's what we will do in this course in much more detail. So let me stop here. Thank you so much.